All right, hello everyone. So we got our last chapter of organic chemistry. This is the last bit of new material you guys will be learning in your organic chemistry careers here at Fresno City, maybe your whole life. And we're going to finish off with organometallics. A few of these we've gone over: the organomagnesiums, aka Grignards, and organocuprates, aka the Gilman reagents. And then a new one, organolithiums, although we'll see they're pretty easy to deal with. So first start with some of the ones we know, introduce a few new reactions, and then we're going to learn about some new ones. So first of all, one of the things to remember when we're talking about organometallic compounds, we're talking about copper bound to some carbon bound to some metal. And the reason why this is kind of a big deal is because these metals have really low electronegativity compared to the non-metals. So we don't really usually think of carbon as being very electronegative within the context of all the other elements we're used to talking about in organic chemistry, like oxygen and nitrogen and the halogens. But in comparison with these metals, it is. So in these compounds, you will have a partial negative charge on the carbon and a partial positive charge on the magnesium. Okay, so again, this organolithium compound is new. We're going to see that it is pretty much equivalent in behavior to the Grignard reagents or the organomagnesium compounds, right? So again, this was a Grignard. And this guy we learned about as well. This is a Gilman. Okay, and if you remember, we said that the Grignard was a very strong nucleophile, and the Gilman was a weaker nucleophile. And this can be explained by simply the trends in electronegativity. Copper is more electronegative than magnesium, right? So the difference between copper and carbon is less than the difference between magnesium and carbon. Right, so the partial positive charge on the Gilman copper and partial negative charge on the carbon are smaller in a Gilman than in a Grignard. Okay, and so because of this, well, so first of all, just to review some of the reactions we saw. Again, Grignard we said were strong nucleophiles, whereas Gilmans were weaker nucleophiles. And so where this was illustrated most clearly was with regard to our carboxylic acid derivatives, in particular the acyl chlorides. We saw that a Grignard will actually react twice. You know, first it will add on and create a ketone, but then Grignards are strong enough to react with ketones, so it will undergo another round of addition. When we had the Gilman, it was strong enough to react with that highly reactive acyl chloride, but then it's not strong enough to undergo another addition with the ketone that's created. Okay, and again, it has everything to do with these electronegativities. The other way that we saw the Gilman sort of differing from the Grignard is that it will attack these enones or alpha beta unsaturated compounds at the beta carbon, right? So this electrophilic beta carbon. I guess just to really review here. The organomagnesium or the Grignards, they're too reactive to react at this beta carbon. Instead, they will react at the carbonyl carbon, just like they would with a normal just like they would with a normal aldehyde or ketone. So if we had an MeMgBr followed by H2O for this same compound, what we would expect is something like this, where here is the new methyl group that's been added. Different from up here with the organocuprate, where it gets added to the 1,4 position. Okay, so this is another sort of difference that we saw comparing the Grignards to the Gilman. Okay, and remember that in these reactions, what's happening is you have this very polar bond where the electronegativity is sitting on the carbon, And so the carbon's playing the role of the nucleophile. You can think about these as being ionic bonds where carbon is actually holding on to all of those pair of electrons. Again, these organolithiums, we haven't seen them before, but we're going to treat them exactly the same as a Grignard. Same type of reactions, all that good stuff. One of the things that we haven't explicitly talked about are the limitations of what can be on a Grignard. It turns out that the other part of a Grignard, so it can be an alkyl group, an aryl group, meaning that it can be directly attached to a benzene ring, or a vinyl group. So remember, vinyl refers, if we're talking about a alkene, the vinyl carbons are those right there. So a vinyl Grignard would be something like this. This is actually, it sounds like it's kind of restrictive. It's actually pretty class. This is going to be a big part of this chapter, is a lot of these organometallics are going to have limitations on what can be on the back half, okay? The other two big groups that are missing from this list, just to keep in mind, are benzylic groups. So that would be, so let's just, benzylic would be not directly on the ring, but one removed from a benzene ring, as well as allylic, which is again referring to double bonds not directly on the double bond, but one removed. Both of these you cannot use with a Grignard. You actually, truth be told, you can. You just get these complicated rearrangements that go down because of resonance. So we're going to exclude those as part of our Grignards. But those are going to be the five main classes that we're going to see: alkyl, aryl, vinyl, benzylic, and allylic. For Grignards, you cannot use, for both the organolithium and the organomagnesium, you're restricted to alkyl, aryl, or vinyl. So this is how we would create an organolithium compound. Pretty straightforward. You take your alkyl halide and then you toss in 2 equivalents of lithium metal. You need 2 equivalents because one of them goes on to the alkyl group or the aryl group or the vinyl group, creating your organometallic compound, and the other one is attached to whatever halogen. Okay. This is pretty similar to what we saw happens with the formation of Grignards as well. You just toss in some solid magnesium to a halogen halide compound, and you're usually doing this in the presence of an ether. That's what this is doing right here. It's your solvent. And again, you only need one equivalent because unlike the organolithium, magnesium just kind of inserts itself in that bond there. I shouldn't draw that arrow because it's not like it's an electron pushing sort of thing. We're actually, good news about this chapter, we have no reaction mechanisms that we're going to be learning about. Metals are just really complicated with how their electrons flow. So we're not going to worry about any electron pushing for this chapter. So it's kind of nice. Okay, and again, you could see the alkyl, the aryl, or the vinyl possibilities that you can have for a Grignard. This is, yeah, so again, the solvent is thought to actually play a pretty important role. You cannot have any sort of a protic solvent, so you use something like an ether. THF can also be used. It's actually thought that the electron pairs on the oxygen and the ether play a really important part in stabilizing the Grignard. Not really something we need to worry about too much. One very important consideration when thinking about Grignards as well as organolithium compounds is that they are strong bases. So any protic, the presence of like any donatable protons are going to mess up your Grignard in that your Grignard's going to react, right? So one of the things that we talked about is you can't have any water present when you're doing a Grignard, because what's going to happen is the alkyl portion or the aryl or the vinyl is going to just steal one of those protons. You're going to be left with like an alkane or something like that. Likewise, you can't have any alcohol groups. So you can't prepare a Grignard when there's an alcohol group present. You would have to, we learned that you can do a protecting group onto that alcohol and then create your Grignard. But can't have that OH because all that's going to happen is It's going to react to that hydrogen. So just to review the reactions that we learned about with Grignards, what happens when you react a Grignard with an aldehyde or ketone? You get that R group attached to the carbonyl carbon, and what was your carbonyl oxygen is now a alcohol. What about when you have a Grignard reacting with, remember these three-membered rings with the oxygens? These are epoxides. So what happens is this guy goes and attacks this carbon, and then that ring opens up. So again, we have an alcohol group, but importantly, our Grignard, that R is located exactly 1-2 carbons away, as opposed to being directly attached up there. What about with CO2? This is one that we learned about specifically. Will actually create a carboxylic acid when a Grignard reacts with carbon dioxide. When Grignard reacts with a ester, we can also sort of throw this in the same category as an acyl halide. What happens is you have 2 additions of that R group onto that carbonyl carbon, right? So you get one first, that leaves you with the ketone, and then that follows up with the second one. And lastly, what happens when you take a Grignard and react it with a nitrile group, cyano group? Actually get an aldehyde or ketone. Now, why doesn't it undergo 2 additions like we talked about before? Because actually the first step here will create, this imine. And then when you do your second step and you hit it with that acid, that's when the imine nitrogen is replaced with an oxygen, right? So you can't have a second round of Grignard addition because it doesn't occur, the ketone doesn't exist until you get to the acid step. Okay, so now preparing a Gilman reagent. We talked about Gilman reagents, how they react. Remember, Gilmans are when you have these R groups attached to copper. You actually have 2 of them attached there, but only one of them will react. But these actually start with an organolithium compound. So the first thing you do is prepare an organolithium and then react it with copper in order to get your Gilman reagent. I said, if I just want to go back real quick, I kind of said that you can keep these 2 in your mind, the organolithium and the organomagnesium. That's absolutely true. They react in the same reactions. The list of reactions for the organolithium are the same as the organomagnesium. Truth be told, nobody's going to use an organolithium when they could just use a Grignard. Lithium costs about 10 times as much as magnesium. So the only time that you're going to use an organolithium is in order to prepare a Gilman. Okay, or to prepare some other sort of step. You would never really use it in practice in place of a Grignard, but let's say that you do get such a question thrown at you on the Wiley Plus, you can keep this in mind that the organolithium will undergo the same reactions as the Grignard. Okay. So anyway, the real use for an organolithium is in order to react it with this copper compound and get to this here. This would be copper 1 chloride or copper 1 bromide or something like that, copper attached to a halogen, is in order to get your Gilman. Okay, so first of all, the R groups on the Gilman are the same limitations as the R groups on the organomagnesium and the organolithium compounds, because you have to start with the organolithium. So again, we're talking alkyl, aryl, or vinyl. Okay, so those are our limitations on our Gilman. And then we've learned about some reactions with a Gilman already. Again, we sort of already went over these 2, but just to review again, what happens when you react it with an acyl chloride? You have just 1 addition of that R group. What about when you have an alpha beta unsaturated ketone or aldehyde and enone? You're going to get attachment to that beta carbon. So now this is the only real new reaction of this chapter is what's called a coupling reaction that takes place with an alkyl halide. So this is sort of another powerful reaction because you're forming a carbon-carbon bond, but notice that there's no oxygen or other functional group that's going to be involved here. You can just have an alkyl halide and react that with your organolithium, okay? We talked about the limitations on the Gilman R group, has to be alkyl, aryl, or vinyl. Now let's talk about the limitations on your alkyl halide that you're going to use. Has to be methyl or primary alkyl group. So it's actually the same as the other R group with the extra stipulation that if this is an alkyl group, right, so these would just be considered alkyl groups, but it has to be a methyl or a primary alkyl group, as well as an aryl or vinyl, okay? So yeah, just keep that in mind. And what's going to happen is you're very simply forming new bonds here. So again, this is sort of a powerful way of forming carbon-carbon bonds because there aren't any other functional groups that necessarily have to be present, right? So for example, if your R was, you know, a methyl group or something like that, you've now created a very simple alkane using this Gilman as an alkyl halide. And so how do we go about predicting products? Fairly easy. Your R group's just going to be attached to the electrophilic carbon that that halogen is attached to, right? So here's my new bond is going to be with this carbon here and my R group. Same if it's a vinyl, this carbon here and an R group. Similar to some of the previous chapters, one of the hard parts of this chapter is going to be you're creating these big ugly products, right? So counting carbons is going to be like your best friend in this chapter to make sure you have the right products. With regard to the other alkyl groups, tertiary alkyl halides or secondary alkyl halides, the real problem is that you have competition with elimination reactions. So you're not going to get these purely substitution products. So that's why we've limited the R group that can be on our alkyl halide. Other nice things about these types of reactions, I mean, they're the Corey-Posner-Whitesides house reaction. I'm not going to call it that. I have no idea. I don't know those people. Whatever. That's technically the name for the reaction. I wouldn't worry too much about memorizing those guys' names. But anyways, one of the other nice things about these reactions is the fact that they will preserve any sort of stereochemistry in either R group. Right, so if your organocuprate, remember this is this R, this is now a vinyl organocuprate or Gilman reagent. Well, by R, I mean that's the group that's attached here. Notice how it has the E stereochemistry associated with it. And then I have an alkyl halide, this was the blue R group, that has a Z stereochemistry associated with it. Both of those stereochemistry of those double bonds will be preserved in my product. So I'll have one E double bond and one Z double bond, okay? So again, nice thing about these are that they're stereospecific reactions. The stereochemistry of either of those groups are going to be preserved. The other nice thing about about these reactions are they're very specific to the reactions of the alkyl halide group, right? So there's some other functional groups that you can include on these, the alkyl halides that aren't going to be reactive with your Gilman reagents. So an ester is not reactive. Remember, an acyl chloride is, but an ester is not. So you can have an ester group on there, you can have a ketone group on there or an aldehyde group on there, and that will still be compatible with these types of reactions, right? So any ketone aldehyde, an ester or an amide group, and I guess we'll keep it blue because it would be that portion of the molecule, not an acyl halide. You also can't have any acidic protons. So it can't be a carboxylic acid or an alcohol. Those will react because this can still play the role of a base. No acidic protons. Okay, so in terms of a retrosynthetic sort of idea of how you would approach this, you have this compound and you want to figure out how to make it. Sometimes it might not matter which half you decide to be your Gilman and which half you decide to be your alkyl halide, right? So for example, these were both benzene rings, something like this. Well, both of these chunks here can be aryl groups, right? So the retrosynthetic problems in this chapter, what you're going to have to consider are what are the limitations of each of these R groups. When would this be really important is, let's say that we have something like this, where this is my new double bond that's formed, or my new, not double bond, single bond that's formed. The limitations on R are alkyl, aryl, and vinyl. And the limitations on the alkyl halide portion are similar, except for it has to be methyl or primary. It can also be aryl or vinyl. So that means that for this particular case, if this is the bond that's formed, let's just code it this way. This section here has to be my organocuprate. And this section here will have to be my alkyl halide. I can't switch them because otherwise I'd have a secondary alkyl halide that I was working with. Okay, so these retrosynthetic problems are going to be a big portion of this chapter, and that is why keeping in mind the limitations of these R groups is going to be so important. So just to summarize, we know how to prepare organolithium and organomagnesium compounds, kind of just as straightforward as tossing in solid metal lithium or solid metal magnesium in with an alkyl halide. To prepare a Gilman, you actually first go through that organolithium and then react it with like copper 1 chloride. When it comes to the Gilman, we learned a new reaction. So we have our old reactions for the Grignard and our old reactions for the Gilman. When it comes to this particular chapter, we learned yet another new reaction with the Gilmans, which is quite powerful in that we can create quite a bit. And that is to react it with an alkyl halide or aryl halide or a vinyl halide, to react it with some sort of a halide here, remembering the limitations on these R groups. And these reactions can be very powerful because they are stereospecific, i.e. you will preserve the stereochemistry in your two starting reagents.